when you finally understand what a digital twin is. So you're building complex systems. Maybe they're even hardware intensive. One of the key enablers to move at a pace of relevance is the ability to ensure that your guesses and potential changes are correct. And more importantly, that they will behave the way that you believed in the first place. You want to be able to run small incremental software changes multiple times a day on the digital representation of your system to see how they perform. Additionally, you want to know exactly how your system is going to behave before even bending metal. You don't want to go through the headache of physically building a prototype to realize that the wings won't be able to create enough lift for your next generation plane you've been working on, right? You want to validate assumptions fast, and you want to avoid finding problems late in your life cycle. The earlier, the better. That's where digital twins come in. Pretty much every industry is concerned, from automotive to space to healthcare to constructions, even manufacturing. If you have not checked our video on SpaceX versus F-35 and how SpaceX is able to run 17,000 build of software a day digitally and 3 hardware-in-the-loop testing a day, do that now. The first practical implementation of a digital twin came from NASA to improve the simulation of spacecrafts back in 2010. So what is a digital twin? A digital twin is a virtual representation of a system, often a complex system. From mechanical hardware to electronic hardware to connectivity to cloud services to sensors to software and more. All of these different domains have cross dependencies. You want to be able to be modular and flexible for both your hardware and software. Maybe you even want to swap a piece of hardware for another or add a new software capability. For that, it is important to be able to emulate and know for a fact that those changes are not going to break your system. This will enable the simulation, integration, testing, and monitoring of your system. For example, it could be that your new hardware module does not support the same communication protocol, or maybe that the new mutual TLS crypto that you're bringing to finally make your product's communication secure is not compatible with your existing compute capabilities. By rapidly iterating virtually instead of by bending metal and by finding out issues before the fact, you save a tremendous amount of time and money, of course. This will enable you to compare options as well, kind of a A/B testing baked-in capability. You can now turn guessing into predicting. Okay, so that's all good, but building an accurate representation of your system is not easy. It's a never-ending maturity journey. Many companies pretend they can streamline that process, and that can sometimes be true to some degree. But you certainly don't want to reinvent the wheel, as you must be able to emulate real-world behavior and dynamics. Things like real-time physics, gravity, wind, etc., based on your use case and the importance of those different external factors, for example. From each phase of your product lifecycle, digital twins will bring a continuous learning and improvement opportunity from design to build to operations and even maintenance. Of course, for this to work, you will need to collect lots of data and leverage artifacts created across your product's lifecycle. For that, data must be open, and you must leverage an open architecture to enable proper integration across all these domains and, more importantly, avoid vendor lock-in. Product drawings and engineering specifications have progressed from handmade drafting to computer-aided design to model-based systems engineering. A digital twin can leverage real-time data from sensors and other IoT devices to capture telemetry from existing deployments and earlier versions of your systems as well, to bring tangible lessons learned and valuable insights in terms of component lifespans and more. A digital twin is really a data-informed model of that complex system. But where is all that data coming from? To find out, Let's have a look at the concept of a digital thread. A digital thread is a data pipeline that correlates all the information generated from these life cycle stages, from design to analysis to inspection to manufacturing models to sensors to service and maintenance data. It is the authoritative data, and it is used to describe the traceability of the digital twin back to the requirements and each modules and controls of the system. An additional benefit of having a digital twin is the ability to automate the generations of all these artifacts, from design documentation to manufacturing model for 3D printing and molds and more. More importantly, those are never stale, as they are automatically and continuously updated. By streamlining the design, build, and operations of a system, this enables feedback loops between organizations, products, and customers. It makes data sharing and, more importantly, insight sharing easier. The connectivity between your various supply chain vendors can be increased. More importantly, they can continuously check the behavior of your system by simply using the digital twin. Teams can also leverage digital twins to start training end users on a product before they're even made. That's a game-changing differentiator to streamline the adoption and learning that comes with new, complex technologies. Effectively, you can see pilots nowadays virtually fly a new aircraft before it is delivered by using an approved simulator. Of course, you would want to be able to demonstrate that the software also runs on your final hardware. Your digital twin is only as good as its accurate representation. So let's face it, it's not going to be perfect. That's where hardware-in-the-loop testing comes in. Stay tuned for our next video on hardware-in-the-loop testing. We're also working on an entire video series that will cover architecture and modeling and simulation with a special guest. There you have it. From your design, manufacturing, certification to real-world deployment, digital twins are continuously leveraged to remove unknowns and impediments. Effectively, they accelerate the delivery of a complex system. Developing digital twins is getting cheaper, and digital twins make it much cheaper to test, predict, and solve problems on a virtual representation rather than testing on physical models and waiting for physical products to break before taking action. By enabling modularity of your software, but more importantly, of all of these manufacturing models, you gain the ability to tweak models and systems endlessly while ensuring that your system is built with flexibility and open architecture in mind, all before even bending metal.